This is a workthrough of Problem 1 on Exam 2 in Module 1, which is on page 24 in the book Problem Solving Guide for Electromagnetism and Optics, 3rd edition. Problem 1 is there are minus 2 nanocoulomb charges at the points 1 centimeter, 1 centimeter, 2 centimeters, 1 centimeter, and 3 centimeters, 1 centimeter. What is the electric field at the origin? Since the electric field is a vector, we need to give magnitude and direction. As always, we like to start with a good diagram. Here's an XY plane, XY axis. The first charge is at 1 centimeter, 1 centimeter, which is right here. Let's put one there. 2 centimeters, 1 centimeter is the position of the next charge. And then finally, 3 centimeters over, 1 centimeter up. We want to know the electric field at the origin. So let's think about the electric field at the origin from these three charges. They're all negative. Electric field produced by each of them is directly toward them because the electric field is the direction a positive charge would go. So we have three vector fields directly towards each one of those charges. The charges are all minus 2 nanocoulombs. So the closest one is going to produce the strongest field. So we can put that one in. Just a qualitative vector in that direction. We're not too worried about the exact length. We just want to get the relative lengths. Good. This charge is producing a field at the origin in that direction, and it's significantly smaller. And finally, this guy is very far away, so he has a small field directly toward it. We have to sum those three electric field contributions to the electric field at the origin to get the net electric field at the origin. The magnitude of the electric field at a distance r away from a point charged q is given by this equation. We have all the q's. We need the distances. We need the distance each point is away from the origin. Then we can calculate the strength of these vectors. To get the distances, we can use the Pythagorean theorem. This charge is 1 centimeter over, 1 centimeter up. We want the hypotenuse. So a squared plus b squared is c squared. The distance from the origin to the point 1, 1 is 1.414 centimeters. This charge is 2 over, 2 centimeters over, 1 centimeter up. That's the square root of 5 centimeters from the origin. And finally, the last charge is 3 centimeters over, 1 centimeter up. That's the square root of 10 centimeters from the origin, which is 3.162 centimeters. So we have the distances, we have the magnitudes of the charge. We can calculate the magnitudes of the electric field vectors produced at the origin. Magnitude of the electric field, kq over r squared. We have the k's, the q's, and the r's. There's the constant. I converted everything to SI units. So I have coulombs and meters. 1.414 centimeters is 0.01414 meters. And we get that this electric field vector length is 89,900 newtons per coulomb. Moving to the second charge, it is 2.236 centimeters away. The magnitude is the same. This vector length is 35,960 newtons per coulomb. And finally, the last one is 3.162 centimeters away, the same magnitude. This electric field vector length is 17,980 newtons per coulomb. Now we have the magnitudes. To add them up, we need the directions so we can get their x and y components. To get their directions, we can use the arctangent function. Tangent is opposite over adjacent. So the theta of charge number 1 from the x-axis is 1 centimeter divided by 1 centimeter. The angle whose tangent is 1 centimeter divided by 1 centimeter, that's 45 degrees. For this charge, we need the angle whose tangent is 1 centimeter divided by 2 centimeters, which is a half. The arctangent of a half is 26.57 degrees. The tangent of 26.57 degrees is 1/2. So this angle, this vector is 26.57 degrees above the x-axis. Finally, this one is 1 centimeter up, 3 centimeters over. The arctangent of 1/3 is 18.43 degrees. So now we have the angle between this little vector and the x-axis. With the vectors, with the angles, we can get the components. Let's start with the horizontal direction. We're going to get the horizontal contribution from this guy, then from this guy, then from this guy. Cosine is adjacent, so we have 89,900 newtons per coulomb. Cosine 45 degrees, that's the side adjacent to the x-axis. 35,960, cosine 26.7 is the x contribution from this vector. And finally, 17,980 newtons per coulomb, cosine 18.43 degrees is the horizontal contribution from this vector. We can calculate what these contributions are. 63,570, 32,160, 1760. We add them all up, and we get the electric field in the x direction at the origin, 112,800 newtons per coulomb. Now we're going to do the vertical direction, up and down. 89,900 newtons per coulomb, sine 45, 35,960 newtons per coulomb, sine 26.7. We're getting the opposite side, the vertical side. And finally, 17,980 sine 18.43, this little guy right here. We can calculate the magnitudes of the contributions and sum them up because they're all in the same direction. They're all pointing upwards, and we get 85,330. This type of calculation is very important to know how to do, so let's break it down and do it slowly, one field at a time. So, charge 1 at 1, 1 produced a field of 89,900 newtons per coulomb at an angle of 45 degrees above the x-axis. So, the horizontal component of the field is EX1. The horizontal component in the x direction, that's from charge 1, 63,570. The vertical component, 89,900 sine 45, which is also 63,570. We can draw a diagram. There's the charge, there's the field, there's the origin. We want to get the horizontal component, the vertical component. We use sine and cosine, and we get these two vectors, which are 67,530 newtons per coulomb long, 570 newtons per coulomb long, and then we can get rid of this one because this one, these two replace this one. So we went from here to here, and that's what we want to do. For the charge at 2, 1, we have 35,960 newtons per coulomb at an angle of 26.57 degrees above the x-axis. The horizontal component, we use the cosine, is 30,160. The vertical component, we use the sine, that's 16,080. So here's what we did. We started with that. We got the horizontal component and then the vertical component. And then we got rid of the vector to get this. We went from here to here. The last one, the charge at 3, 1, we calculated it has a magnitude of 17,980 newtons per coulomb at an angle of 18.43 degrees above the x-axis. The horizontal component, 17,060. The vertical component, 5,680. Here's the diagram. There's the field, 18.43 degrees above the x-axis. Got the horizontal and the vertical components, and then we got rid of the original vector, leaving only E sub y and E sub x. Now let's add the x directions. The first charge has a field in the x direction, 63,570. The second charge, 32,160. The third charge, 1760. The total horizontal component is, add up all the x directions, 112,800, and we can see what happens in the diagram. These are the 3 arrows. They're all pointing to the right. We can put them head to tail like this, and then we want to get the total length, so we just add them up. That vector, 112,800 newtons per coulomb. The vertical components, EY1, 63,570, EY2, 1680, EY3, 5680. Total vertical component, we just add them up. They're all pointing up, And here they are. There's 1, there's 2, there's 3. That's the littlest one. And we can just stack them on top of each other to get the total length. And this total length is that vector, 85,330 newtons per coulomb. So our goal is to sum these electric field vectors. Here's what we did. Got the magnitudes, got the angles, got the horizontal and vertical components, summed the horizontal components, summed the vertical components to get the magnitude of the electric field at the origin. So here's where we started. After we get the 3 magnitudes in the 3 directions, got the horizontal and vertical, summed them up, and then we got this figure. Here's where we are now. 112,800 in the x direction, 85,330 in the y direction. And the reason why we do this is because now we can use the Pythagorean theorem to get the magnitude of the electric field at the origin. E is e sub x squared plus e sub y squared, square root. So we can calculate the electric field at the origin. It's 141,000 newtons per coulomb. And we can get the direction of this field with the arctangent function. So we have the opposite side, which is 85,330. The adjacent side is 112,800. The angle is 37 degrees above the x-axis. So the answer is the electric field at the origin is 141,000 newtons per coulomb, 37.1 degrees above the positive x-axis. And we can draw it in. There it is. That's about what we thought. Those 3 vectors, 1, 2, 3, add up to that vector. That's the answer to problem number 1 on exam 2 in module 1.